We're going to try to prove something that involves some slightly uncommon notation. So let me just use a numerical example to illustrate what this double vertical bar notation means. 3 divides 45. If you want to, we can write 3 as 3 to the first power. And that's clear since 45 equals to 3 times 15, right? But notice we can say a little bit more because 3 is not the lowest power of 3 that divides 45. We can go a step further and say 3 squared fully divides or exactly divides 45. And notice we use the double vertical bar notation here. And of course that's because 45 is equal to 9 times 5. So this is the largest power of 3 that is a factor of 45, and we use this double vertical bar notation to connote that. Okay. Now, what we're looking for this particular problem is we want to find the n, which will be unique, that fully divides this huge number 3 to the 128. You can't even pronounce that number or say it, you know. So we're looking for the maximum n such that 2 to the n divides the quantity 3 raised to the 128 minus 1. Okay. Now what we'll be using really here is just we'll be using repeatedly this very well-known result, difference of 2 squares. Okay. Super common result, has a geometric proof, algebraic proof, you know. So we're going to use it again repeatedly here. Now, if you take a look at this, let me scroll down just a little bit here. So this is the object we're interested in. We want to show that this is always what the highest power of 2 is that divides this. That's a factor of this number, this huge, huge number. Now notice, and I won't have to write this down too many times, but 3 raised to the 128th. Okay. 3 raised to the 128th power is a perfect square since it's equal to 3 to the 64th quantity squared. And remember just your laws of exponents. If you have 2 copies of 64 copies, you have 128 copies, right? So 3 raised to the 64th, again raised to the squared, is going to be 3 to the 128th. And you can see that's what we did right here. This would be your a plus b. This would be a minus b as far as this identity goes, right? But we're not done, right? Notice that 3 to the 64th can be written, 3 to the 64th minus 1 can be written as 3 to the 32nd plus 1, 3 to the 32nd minus 1. And I'm not going to talk you through all of this. It's you can see the pattern. It works out nicely to where we end up with this expression. The expression we're trying to test for divisibility is equal to this product of factors. Okay. And again, I tried to show as much of the work as possible, but I'm pretty sure I did all this right. Now, it turns out there's a very special result that we can use now. It turns out each one of these parenthetical quantities is divisible by 2 exactly. And here's the result. And again, this is something we could prove also. It's very clear that 2 divides 3 to the 2 to the n plus 1. You can verify that. Just check 0 and 1. You get 2 and 10. And it works for 0 and 1, which are the only divisors or the remainders when dividing by 2. But also know that it's very easy to show, and I'll just write down and you guys can verify it. 3 raised to the 2 to the n plus 1 is not congruent to 0 mod 4. Another way of saying that is that 3 to the 2 to the n plus 1 is never a multiple of 4. Okay. Now the way to check that with congruence arithmetic, just and again I'll show you right here. Just if n is equal to 1, which is one of the legitimate remainders, when you divide by 4, right? If n is equal to 1, what do we get right here? We get 10, right? So I should say that I should say for all n right here probably, I guess, to be careful with the universal quantifiers. For all integers n, for all probably non-negative integers or positive integers maybe. But for n equals 1, this evaluates to 10, right? That would be 9 plus 1. And that certainly is not a multiple of 4. Okay, that certainly does not equal to, another way of stating this, 4m, right? Okay, so we know that 2 divides this exactly because 4 is not a factor of this for all n. That's what we just proved. So that's more or less the crude proof of this lemma. But what does this lemma do for us? Well, notice all of these 64, 32, 16, 8, and all the way across are in the form 3 to the 2 raised to the n. These are all powers of 2, right? So it's just a counting exercise. Look, we have 1, 2 divides this exactly, 2 divides this exactly, all the way across. So let's count. 1, 2, 3, 4, 5, 6. Oops, we have 4 here. That's 2 times 2, right? So again, let's count. 1, 2, 3, 4, 5, 6. All of these 6 factors are divisible by 2. So far it's 2 to the 6th. But this is going to make it 2 to the 8th because this is 2 times 2 or 2 squared. And finally we have another. This is just 2 directly, right? So again, let's count. I'll just do it like this. 1, 2, 1. And this is the number of times 2 divides. This is 2 dividing this quantity, right? So if you add all these up, what do you get? 1 plus 1 plus 1 plus 1 is 6 plus 2 plus 8. So we get 9. This all adds up to, sums up to 9, right? And it's understood multiple addition operations going on in here. So what do we just shown? We've shown that 2 to the 9th power divides, what was it we were interested in? 3 to the 128th, okay? 2 to the 9 divides 3 to the 128th. Minus 1 exactly, and that's the proof. That finishes it, folks. 2 raised to the 9th power. But this lemma, combined with repeated application of the difference of 2 squares algebraic identity, is what proved it for us. So that's it. We're looking, so n equals 9 is the answer. Okay. Again, y'all, to me, this stuff is just fascinating because just think about how big 3 to the 128th would be. All right, I mean, try to do that. Even with a calculator, it wouldn't even display on your calculator. It's too big. It would overflow your calculator, or it would lose significant digits, right? So, but we know that 2 to the 9th, which is what, not that it matters, 2 to the 9th, I think, is 512. Okay, so 512 is the largest power of 2 that divides this huge number. Anyway, thank you for viewing.